So we want to continue working on Network Plus, and we're going to talk about IPv4 and classful addressing, meaning publicly routable addresses. Okay? So when we think about what those, i.e. classful addressing or addresses are, let's kind of look at IPv4 is a 32-bit binary address. Okay? It's made up of 4 what we call octets. An octet equals 8. So what does that mean? It means I have 8 spaces, then a dot, and then 8 spaces and a dot, 8 spaces and a dot. Okay? So the very first octet is what these numbers up here are. So in a class A, it goes from 0 to 127. And in reality, that's 1 through 126. Okay? And we'll talk about why. 127 is its own animal, and we'll talk about that here in a minute. So if I see anything that's from a 1 to a 126, meaning the address is like 8.8.4.2, this first octet right here tells me that that is class A. Okay? A class B address goes from 128 to 191. So that would be anything like 132.64.6.85. Okay? My first octet, that tells me that is a class B address. Same thing with class C. Class C goes from 192 to 223. This is our most typical address range we use inside of our networks with what we call classless, but we'll get there in a minute. So this is a class C address. Then there's class D. Class D runs from 224 to 239. This is used for multicasting. Those are very specific for multicast addresses. And then there's class E. Class E runs from 240 to 255. These are considered experimental. They belong to the U.S. government, and I personally have never seen one out in the wild. If any of you guys have, let me know, because I've never seen one used. Okay? But these are our classful addresses for, i.e. public IPs. That means they are routable on the internet. Okay? Keep that in mind when we talk about classless. So some of the concepts for IPv4. Like I said, these addresses. So if we take a simple address like 192.168.156, this particular address would be assigned to maybe a workstation or desktop. And along with this IP address comes this thing here that's called a subnet mask. The subnet mask is needed because it will be used, it will take this address and the subnet mask to figure out what is my default gateway. And that, by the way, is my router. Okay, that's the interface that gets me out of that particular segment of the network. So your default gateway is your first hop. That's the first place you have to get to. So we have what's called a network portion of the address. That's this 192.168.1. And then a host portion, the individual machine. So what that means is that when we look at this subnet mask, this 255.255.255, those are all, that octet, they're all ones. Every bit that's turned on, that means that portion of the address or the network portion is locked down. It's not going to change. All of the rest of the addresses, i.e. this, I can have 56, 57, 85, 192, etc. Okay? But the first portion doesn't change for that particular network. So like I said, it is a 32-bit binary address, all ones and zeros. We represent that as what we call dotted decimal. That's for you and me. Your machine has no idea what a 192.168.1. whatever is. It doesn't know what that is. It only recognizes this. Okay? So what we do is we represent it like this so that we understand it. So what I want to do is let's see here for a second. Let's do this. Let's take a look at what that means. Let's take an address. Let's say 192.168.1, and we'll just use that one, .56. So now let's just isolate for a second one portion of this right here, okay? Where does that number come from? If you remember, this is an octet, which means or equals 8 spaces. So let's draw 8 spaces. 1, 2, 3, 4, 5, 6, 7, and 8. Each one of these spaces has a number that represents it, and this is binary. So binary only has 2 numbers, 1 and 0, but those numbers double each time. So it looks like this: 1, 2, 4, 8, 16, 32, 64, and 128. When we add all of these up, they equal 255. Okay? Now, something you have to remember, and a lot of people get confused here, is it's actually 256. How is that? Because it's 0 through 255. 0 is not nothing, it's a placeholder, okay? And in computing, when we think about, if you were programming, the very first space or place is a 0, right? Then 1, then 2, etc. So here, how do we get to this number 192? Well, I turn on this bit, that's 128, and I turn on this bit, so I have these two, I add them together, they equal 192. The rest of these are zeros. Okay? So those are all zeros. And now let's look at another one. All right, so let's go to, where does this 168 come from? Actually, I didn't mean to do that. Let's draw those up here again. 192, 168, 156. So where is this 168? Same thing. I'm going to turn on this bit. Can I add 64? Nope, that's too much. That's a 0. Can I add 32? Yes. We're now at 160. Can I add 16? Nope. Let's add our 8. There's our 168.0.0.0. And so that's the binary for 168. Okay. So now we're getting an understanding of where that comes from. So now our subnet mask, let's throw that in there. So our subnet mask being 255.255.255.0. This is a typical what we call a class C network, okay? And these 255s mean these are all ones. So this is just a single octet, okay? And there would be 4 of these, one for each one of these sections. So if it's all 255s, that means it's all ones. That means it's locked down. So that portion of the network is our network portion. And then that leaves me this section over here as my host portion. Now, my host portion, you notice here, that's a 0. So that means that all of these start out as zeros. And if I add all that up, that equals 255. So what does that really mean? That means that I have the possibility of 256 minus 2 equaling 254 available addresses. Now, many times you will see this. Let me clear some of this up. All right, so many times you will see this address up here represented instead of showing this 255s. And you may have seen these addresses and wondered, what in the world is that about? And it will actually look like /24. Well, what does that mean? That means that the first 24 bits within that 32 bits are all ones, i.e. 255, 255, 255. That means that the last bit, or the last 8 bits rather, are zeros. So that means I have 255, and remember it's 0 through 255. Now why did I use this formula here? 256 minus 2. Because 0 through 255 is the same thing as saying 1 through 256, okay? Remember I have a network portion. So I have a network ID and I have a broadcast ID. The network ID is, in this case, 192.168.1.0, and that's where you see that /24. There's my network ID, and my broadcast ID is 192.168.1.255. These two addresses cannot be assigned to any machine or any host, okay? One is the network, one is the broadcast. They cannot be assigned to any particular machines. So that's my -2, right? The first and the last. Everything in between. So everything from 1 to 254 I can use, all right, in this last octet. All right. So now, there's some other things we can do here if I want to start cutting it down. So I'm just going to address some of this. When I start cutting down and what we call the CIDR notation, right? Or classless interdomain routing. What if I don't need 254 addresses? Well, let's say I need to break that into 2 subnets. So I could do what's called a /25, and that means I'm going to turn this first bit on. Okay, so I just split that 256 into 2. So what I really have now is I have the possibility of 2 networks, and the first network is 0 through 127 in that my address space, and my second network is 128 through 255. This is my network ID. This is my broadcast ID. So I have, in reality, 1 through 126 and 129 through 254 that I have available to me in those 2 networks. So that's a /25. Now I want you to see what happens with my subnet mask here. It becomes 255.255.255, but my last octet is no longer 0. It is now this number, 128, okay? And as I progress and carve this down smaller, it's going to change, all right? So let's move some of this. And I'm going to write some of these. I'm going to do them one at a time. But we're going to, let's just change that for a minute. Let's make that the 0. So now let's do a 26. Okay. So now if we came along and we turn on these 2, I now have the possibility of 4 little networks. Right, I have 0 through 63. This number will always be the size of the network. Okay, it'll be like 1 less here, but it's not. So the first one's 0 through 63. Then I have 64 through 127. And it just keeps going like that, all right? So this, now, is this 64 right here? No. I'm going to add those together. So this becomes 192. Okay? So I can always look at my subnet mask and tell you what size of the network is, or I can look at this and tell you how many bits are turned on, which tells me what that is. So for example, if I needed to know what if this address was 192.168.185. Okay, so it's 85 is the host. And the question was, what is the default gateway for that network? Well, I'm going to have to go and look and see, where does this 85 fall? Well, it falls between here and here. Remember, this is my network ID. This is my broadcast ID. Typically, your default gateway is going to be the first usable IP in that space. Okay? Now I could make it be any address in that space I want it to be, but just good management practice, we typically use the very first one. So the default gateway for this network would be 192.168.1.65. Okay, that would be my DG. All right, so this is kind of a quick look at this, and I'm going to run through some others real quick as we do this, right? So what if I did a /27? It means I'm turning on this bit, I'm continuing to add. I now have 8 possible little networks, and my subnet mask, it's going to become 224. I could do a /28 where I turn this on. I now have 16 little networks. This is going to change, right? I'm going to just keep adding them up. So this is going to become 240. And if I did /29, turn on this one, I have a possibility of 32 little networks. This becomes 248. And if I turned on this bit, that is a /30. That gives me a possibility of 64 little networks. And this becomes .252. Now, again, we go back to the n minus 2 equals whatever the size of my network is, okay? So if I have this, I have 4 minus 2 equals 2 usable addresses, okay? Why in the world would I ever do that? Well, if I have a router and I have a router, the interface between these two, that has to be in its own subnet. There can be no other devices operating that subnet except those two interfaces, which is why I would do that. So we can take the address space or /24 and we can carve that down in what we call variable length subnet masking. And we can use that one space to create a much smaller space, right, for different areas. Maybe, and I always start with the largest one. Maybe I have, production, and then I have admin, then I have HR, right? And they just get smaller and smaller and smaller as we go, okay? Now, let me go back here for a minute because I wanted to address something else. We were talking about routing and subnet mask, okay? So if I have an address, and let's just go back with 192.168.1.0, and we'll call that /24. I know that's a full Class C address, and I have a subnet mask of 255.255.255.0. Now, in finding the default gateway for this network, there is a process called the and-ing, okay? And what that really means, and the way they normally teach this, is that you're going to take and you're going to convert all of these octets to binary. So you're going to get 1 1 0 0 0 0 0 dot 1 0 1 0 1 0 0 0 dot, and then blah 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 right on down the line, and then you're going to convert this to binary as well, right? And then you're going to look at these and go, is it a 1 and a 1? Bring down a 1. Is it a 0 and a 1? Bring down a 0. Is it a 1 and a 0? Bring down a 0, okay? And you're going to do that all the way across the board, and then you're going to convert that back to dotted decimal to get your answer. And I remember many years ago, and that confused the crap out of me. I hated it, okay? And so I thought there's got to be an easier way to do this, right? There just has to be. So then I thought to myself, okay, let's do some simple math. and ask myself some simple questions. Can I subtract 192 from 255? Yeah, absolutely I can. Bring it down. Can I subtract 168 from 255? Yes, sirree, buddy. Bring it down. How about 1? Yep, bring it down. Can I subtract 0 from 0? Not really, okay? So, I could basically look at this and go, yeah, no. But, so it's just 0, right? But even if this was, let's say this was, let's change that, put our 56 back up there. Can I subtract 56 from 0? And that answer is no, okay? There are no negative numbers in this ballpark, so I have to bring down the 0. Now, where this changes, so that makes it really easy to do, right? Just simple math like that. Where this changes is if this was not 0. What if this was 224? All right, I can still do that portion, okay? I can still do that without any problems. But now I've got to approach this last octet differently. I cannot ask myself the question, can I subtract 56 from 224? I could, but I would be absolutely wrong, okay? So I need to look at this 224 and go, what does that mean to me in terms of the network size? So I'm going to go back to my number line. And I'm going to look at how do I get the 224? 1, 2, 3. Those are all turned on. That tells me that my network size is 32, meaning I have 0 to 31. I have 32 to 63, and I can stop right there. Now, you would continue following that pattern all the way to 255, okay? This is 56. Where does 56 fit in? Well, it fits in right here. So now if the question is what is my gateway, then I know it's not this, that's my network ID, and I know it's not that, that's my broadcast ID. So the gateway would be 192.168.1.33, okay? So that's just a simple way to find that. And what if the question is, what is my broadcast ID? Again, I'm going to go to my number line. What does this equate to? And I may not even see it this way. I may just see it as this, /26, right? And if I just see it as a /26, again, I have to go back and think about my number line and what is the size of that network and what is the ID I'm looking for, okay? So 56 is my individual host. They ask me what is the broadcast. I'm going to have to go, okay, that is 63, all right? So that is just an easy way, right, to do that math. And I just wanted to share that real quick. Okay. So as you can see here, they're breaking it all out. And that's that kind of anding process. Always drove me crazy. And I'm a simple guy. I have to look for easier ways to do things, right, and ways to think about things. So now, CIDR, or classless interdomain routing. How did we get there? Well, let's go back and do a little history lesson. When the internet was first created, it was not created for commerce and business and those things, right? It was originally built for the U.S. government, and it was called the DARPA net. universities and different ones had it. And eventually we got this thing where it was turned loose for commercialism, and we had the IE.com boom. So we began to run out of these publicly available routable IP addresses. And way back in 1998, they came out with a solution. It was called IPv6, right? So it went from a 32-bit address to a 128-bit address. And the reality of that was that most admins looked at it and went, yeah, no, it's not broke. I'm not fixing it. Not working with that. Okay? That's reality. So they went back to the drawing board and said, how do we fix this, right? We came up with a solution and nobody wants to use it. So they said, let's take some of the addresses we have that have not been sold and let's make them not routable on the internet. We'll set the protocols where these addresses are not routable across the public internet and they will be private. So they did that. Within the class A range, they carved out the 10 network, 10.0.0.0, all the way through 10.255.255.255. That is a class A subnet mask of 255.0.0.0. Now, we don't typically use it that way, and I'll discuss that in a bit. Because it's private, we do whatever we want. We typically make it a Class C subnet, so we are only dealing with 254 addresses. That space right there is huge, huge, like 16 million or something. It's crazy, all right? Class B, they carved out the 172.16.00 through 172.31.255.255. That has a subnet mask of 255.255.0.0 or a /16. Right, so back to our CIDR notation, this would be a /8, this would be a /16, this would be a /24, right? Then notice they started with the .16 and they ended with the .31. So anything like 172.15, that's publicly routable. 172.32, that's publicly routable, okay? Those addresses have already been sold. Class C, they carved out the 192.168.0.0 all the way through 192.168.255.255. Again, if you saw an address that was 192.166, that's publicly routable. Or 169, that's publicly routable. So you definitely need to be able to recognize a private address from a public address, right off the bat, okay? Now, loopback. The loopback address that they carved out, remember we looked at here just a couple, let me see, let me go back for a second. Right here, Class A, 0 through 126, and I said, nah, through 127, I said, yeah, that's not quite right. 127 was carved out, and they carved out the entire range, okay, for loopback. We typically only use one, and that's 127.0.0.1. There is no subnet mask. We use that basically to check our IP stack, right, and make sure that it's functioning. And then there's another address set that they carved out, and that's called a PIPA, or the Automatic Private IP Address. This is something that Microsoft uses and others. If for some reason you cannot reach the DHCP server to get an IP address assigned to you automatically, your machine will create one. Now, you can't go anywhere, but it has to have an IP address. And that will be a 169.254.0.0 all the way through 169.254.255.255. So anywhere in that range, it is a private, a PIPA address, okay? Definitely need to know these and where they fit. And these are that CIDR notation I was drawing on the board a minute ago. And these are your subnet masks, right? 128, 192, 224, 240, 248, 252. You need to be able to look at this or that and know exactly what is that range, okay? How many addresses are in that space? You need to know that. It's important, okay? Now, IPv6. IPv6 is a 128-bit binary address. It is typically represented in hexadecimal. So, in numbering systems, let's just talk about them for a second. We have binary. Binary has two numbers, 0 and 1. That's it, okay? So it just doubles each time. 1, then 2, then 4, then 8, etc., etc. Then we have base 10. Base 10 is the numbers 0 through 9. This is what you learn to do math with, right? After 9, you go back to 1 and 0. Then 1 and 2, and 1 and 3, and 1 and 4. And then you get to 1 and 9, and what's the next one? 2 and 0, right? So we're very, very familiar with this numbering system. And there's also what's known as base 16 or hexadecimal. That is the numbers 0 through 9 and then A through F. Much like the very first time as a kid you saw algebra and you went, I was just learning math and now you're putting letters in there with numbers, I'm confused, okay? So after 9, A equals 10, B equals 11, C is 12, D is 13, E is 14, and F equals 15, okay? I.e. placeholders within, that space where they're sitting. All right. So it also has types of addresses. Unicast is 1-to-1, and multicast, which is 1-to-many, right? So unicast is 1-to-1. Multicast is 1-to-many, not 1-to-all, but 1-to-many. So it's not a broadcast. This is what a typical IPv6 address looks like, okay? And it's broken up into sections of 4 like that, followed by a colon. Now, there are methods to shorten that IPv6 address so that it's not so big. There are rules, okay? When you take the test, you're going to be presented with IPv6 addresses, and they'll ask you a question like, which one of these is valid? And they'll give you 4 choices, and you have to look at them and decide, is this the real one? And which one of these is actually the real one, okay? It may be a compressed address, and it may be the full address. So if you know the rules, they cannot trick you, all right? So here are the rules. Any consecutive zeros, like that, they can be compressed into just double colons, okay? Plain and simple. You can drop all leading zeros. Like here you have, let me get a color we can see. A color we can, that's why I don't have that pen, I don't think. All right, yeah, let's do that. So you see you have 0800. Right here it's just 800. So any leading zeros, we can drop those because we know they have to be there. There has to be X number of characters in this address. And just because we don't have them, i.e. represented all the way across, we still know they're there, okay? Like we know that's all zeros. And it doesn't have to be double zeros. It can be 0, 0, 0, 0, colon, 0, 0, 0, 0, colon, 0, 0, 0, colon. And those can just be represented as colon, colon, okay? You can only do that once. You cannot do it twice. So if that address had two different sets of consecutive zeros, you can only do it in the first set, okay? And as long as you know the rules, then there's no way they can confuse you or trick you. Now, these are different types of communications in IPv6. Unicast, one-to-one. It has a globally routable address. Multicast is one-to-many. Anycast would be very similar to broadcast in IPv4. It's one-to-all, okay? There's also a link local address, which is not routable. It is akin or like Microsoft's APIPA address in IPv4. And in IPv6, it will always begin with FE80 colon. Okay? That's how it will begin. And you'll always see it that way. And in fact, your machine will assign one to you. So if we were to do this right here, if I was to pull up a command prompt right here and just do ipconfig, you can see that address right there, FE80. So your machine will automatically assign you, right, that address, period, okay, just in case. And then there are unique local, which is actually private IPv6 addresses. You can subnet IPv6. I know that ISPs will tend to do this. You typically will probably not see this in a local area network. We're going to use IPv4, right? Just being honest. Now, network segmentation. So by default, when we create an IE subnet, we create a security zone, right? We determine rules of who can pass through that router interface to that subnet. So subnetting, we create different areas for like production and admin and marketing and HR and those type of things. We can take that a step further and micro segment the network by creating what's called a virtual LAN or VLAN. Now VLANs allowed us in the early days on IE our switch, any device plugged into that switch was in the same subnet. But then we created these virtual LANs that allowed us to micro segment on that same switch and have different subnets operating on that same switch. We'll talk about that later and how that works, okay? And we also, on the router, can create access control lists because every subnet, when you think about, I've got some devices here, I got some desktops, and these desktops are plugged into a switch. That switch is plugged into a router, okay? This router has an interface right there that is your default gateway. And I can configure access control lists about who can pass through that gateway, right? In other words, rules. On the switch itself, I can do MAC address filtering, right? So I can set up filtering when we configure, like on a switch, I would typically run a command where I'm going to use, the last part of that is actually MAC address sticky. What that means is that when this, say this machine right here, when it first plugged up to that port, it logged its MAC address like normal. Only now it says that is the only device that can communicate right through that. So we're setting up switch port security. We could also do MAC address filtering here, where in our ACL we're saying only allow devices that have, you know, known MAC addresses to pass through this interface and go further. And then we can also create air gap networks. That means I don't have a router. This network over here does not have a router, right? I might have a server over here and it's plugged into the switch, and these guys all communicate, but they do not get outside or go to the internet or anywhere like that, okay? If I have a secure environment, like lab environment, where maybe we're doing some research and development, it's going to be air gapped and none of that's getting out of there, okay? So let's talk about some common ports and protocols. DHCP is our dynamic host configuration protocol. This automatically assigns IP addresses dynamically to the machines. It uses UDP and it uses port 67 and 68. One is the client side, one is the server side, okay? And now we can also configure what's called a static IP address, and we do for things like servers and printers. I don't want to try to figure out where does the printer live today, right? I need to print something and I need to print it now. So we would assign those addresses statically, but we can do that in DHCP in what is called a reservation. So we basically tell DHCP, this printer, I want it to have whatever address you give it the same one every single time, right? You do not allow it to change. DNS is our domain name system. It can use UDP or TCP, all right? It always will use port 53. Now, what does that really look like? Well, it will always use UDP. So whenever you open your browser and you say, I want to go to YouTube, the first thing your computer is going to do is look inside your computer in what's called the host file. Do I know how to get there? Okay. So to give you an example, let me just go back to here for a second and run this command, ipconfig /display DNS. As you can see, it's currently pretty long, right? So this is everything my computer knows and how to reach it, all right? So the first thing your computer is going to do is look in that file and go, do I know how to get there? If that answers no, it's going to reach out to your local DNS server. At home, right, it's going to be your ISP modem that you have, your home router. And does your ISP know how to get there, okay? And that's going to use UDP. But if it doesn't know the answer, and it has to do what's called a zone transfer and go out to like public DNS to resolve like who is YouTube and how do I get there, then that's going to use TCP. Because TCP is a guaranteed delivery and I have to get that information. I can't just take the chance of maybe I get it, maybe I don't. All right. HTTP is the Hypertext Transfer Protocol. This is the protocol for going out and retrieving web content from a web server. It uses TCP port 80. That was the original. It's plain text, so it's insecure. And today we mostly use HTTPS, which stands for SSL, the Secure Socket Layer. And then we added TLS. So pretty much in today's environment, we just talk about like TLS 1.2. We don't even mention SSL anymore. I don't even think the current test mentions SSL, but TLS is built on SSL, so it's still there, okay? It uses port 443, and it uses the public key infrastructure to encrypt and secure that web traffic. And then later on in the course, we'll talk about what does that really look like, and different types of encryption and how that works, okay? SMTP is the Simple Mail Transfer Protocol. This is port 25. This is your mail server. So when you create an email and you send that to, John Doe, this is the port that it sends it out on. POP3, which stands for Post Office Protocol, version 3, it uses TCP on port 110. And that is your email inbox. That's your incoming email. FTP. So FTP is the File Transfer Protocol. Like I said, probably the oldest protocol on the internet. It uses 2 ports, port 20 and port 21. One is the control side, one is the data side, also known as client and server, okay? So you're communicating on one port, you're getting a response back on another. IMAP uses TCP port 143. It stands for the Internet Message Application Protocol. You can think about your Gmail, all right? So it is an online email box. It is not on your computer. You probably, like me and everybody else, you synced it to your desktop, you synced it to your phone, to your tablet, and everywhere else that you connect from. But the actual inbox is up there on a Google server somewhere, okay? LDAP, the Lightweight Directory Access Protocol. This is a protocol. When you go to log in, there's some newer systems today, but LDAP doesn't just take your information over there. It also works with the dynamic link library and calls made in the back end and all of that. So what is LDAP? It is a pickup truck, okay? Get a window in there. It's a pickup truck, which is i.e. the protocol that you put the information in the back of and you carry it over to its destination. That's the way I want you to think about certain protocols, right? They are simply carriers of the information, and that's what LDAP is. It's on port 389, okay? And then there's LDAP Secure. So this is going to move that to port 636, and it's going to use Secure Shell. Because LDAP by itself is insecure. Then there are other protocols like the Media Gateway Control Protocol for things like voice over IP. And it, again, you see it uses 2 different ports, 2424 and 2727. Then there's RDP. This is Microsoft's proprietary remote desktop protocol. This uses TCP port 3389. NetBIOS. NetBIOS is a very early protocol within Windows systems. It uses both TCP and UDP. Uses port 139 for TCP. It uses 2 ports with UDP, actually kind of between, but uses 137, 138, and 139, depending on whether it's TCP or UDP. Is the BIOS system. It's still there, even though today we don't typically use The old master boot record, we use UEFI, which is, you know, the Unified Extensible Firmware Interface. It's protected boot files. But NetBIOS is still running in the background. And Microsoft didn't reinvent the wheel, guys. Each new operating system is built on top of, right, the old one. NTP, the Network Time Protocol, uses UDP on port 123. This is very important for syncing all of your devices together. If you look at the clock on your computer down at the bottom right corner, you're probably getting that information from, if you're at home, it's coming from your ISP through your local modem. And if you are in a network environment, chances are they are not using the ISP. They will deploy an NTP server, and it will get its clocking from the ISP, but then all of the desktops and routers and switches and servers and everything else are getting their clocking from that NTP server, and this is the port on which it does that. And then there's remote shell that allows someone to run commands remotely from the command line. And that will operate on port 514. Telnet. Telnet is a legacy protocol for remoting into a device like a router or switch to manage it. It uses port 23. It is plain text. And today it is a no-no. Which is funny because I saw just the other day, I mean in the past week, some new exploit out in the wild for Telnet. And I thought, okay, why? But obviously somebody's still using it. Secure Shell came along to replace it. It operates on port 22. Secure Shell uses like RSA for encryption, which is a 2048-bit key, and MD5 to hash it, or SHA-1. We'll get more into those later, okay? Now, can Secure Shell be broken? In other words, could somebody hack into it? Yeah, they can. Now, we don't use it like long term. If I have to remote into a switch to check something or make some configuration change, I'm only going to be there a few minutes. And the chances of somebody actually finding that connection and being able to, breach that connection are pretty slim, okay? They would literally have to be monitoring my every move to do it. Now, TFTP. We talked about FTP being the file transfer protocol. It's really good with large files. TFTP is the trivial file transfer protocol. It is not real good with large files. It is good with small files. So if I just took the time to configure, say, a 48 port switch, and I've had to configure every single port and its settings, when I'm done, I'm going to save that to the running configuration, from the running configuration to the startup configuration, so I don't lose all my configs if it reboots. And I'm also going to save it to a TFTP server. Now that may amount to a network share somewhere on the network, or it may just be a file on my laptop, to be honest, okay? And that way, it's going to use port 69, but that way I can very easily recover if I need to. RTP is the real-time transport protocol, delivers media-based data through the network. Can use either TCP or UDP on ports 5004 and 5005. RTSP is the real-time streaming protocol, controls the playback of streaming media. Again, it could be TCP or UDP, most likely UDP, unless it's more secured. It's going to be on port 554. And then there's SIP. SIP is the session initiation protocol. So that will establish connections for media whether it's voice over IP or real-time streaming services like through Zoom or Teams or any of those platforms. UDP will use port 5060 and TCP will use port 5061. SMB, the server message block. It's used for network shares like file shares, printer shares, and things like that, and that is port 445. And then there's SNMP. SNMP is the Simple Network Management Protocol. It is a management protocol for monitoring and configuring devices on the network. It uses port 161, but I will also throw in here, there is another port that it can use, and that is port 162. This is a specific port that is used for a thing called a trap message, TRAP. We'll talk more about that later, but this would be if you have a device out here, like maybe you've got a switch out here, and that switch is something funky going on, and it basically sends this trap message back to the management console like, hey, I need some help, right? Come take a look over here because I am struggling, right? It's a Hail Mary message. So it's unsolicited, and that uses port 162. All right, troubleshooting tools. So things like ICMP. So let me come back and pull back up this command prompt. So if I'm troubleshooting something on the network, and maybe there's some connection issues, well, the first thing I want to do is ipconfig. Do I have a valid IPv4 address? Okay, cool, I do. So all right, that's what I want. All right. Sometimes I can't remember if I'm on Linux box or on Windows. All right, so I have a valid IP address. Maybe I want to do ping. Let's test my IP stack. So I'm going to do 127.0.0.1. And as you can see, I'm getting a response. And I will get a response from all of these, but I'm getting a response from all of them. So let me check my gateway. So let me ping 192.168.12.1. So I'm getting a response back from that. And from there, maybe I try to reach out and I just do, let's just do ping google.com. And of course, I'm getting a response there. Okay. So all that looks good, but maybe the machine is running slow. So I might do netstat and hit enter. And what this is going to do is begin to build me a configuration of all of the active connections. So I can look and I see this address here. That's a public IP address. So I'm going to then ask myself, do I know who this is? Right? I'm going to go out on the internet, do a who is search and things like that. See who that is and should they be connected? Okay? A lot of these are going to be Microsoft running in the background. Then there's Wireshark. So Wireshark, let me go ahead and stop that. All right. So this is Wireshark, and what I can do here is I can look and I could go ahead and start a capture. Now Wireshark will bury you in information really, really fast, okay? So it doesn't take but a minute and it will bury you in information, all right? So I'm gonna go ahead and stop that. And then I can go back and begin to look through this and see what is what, right? So maybe I want to filter traffic and just look for DNS traffic. And now I've filtered it out and I just see DNS traffic. If I just wanted to look at DNS server traffic, don't see a source for that directly. So I go back to DNS and I see that my gateway here and my machine are talking right back and forth, resolving different things. So that's Wireshark. And then of course Nmap. And I will kind of do that later. I'll show you a picture in a minute of what that looks like as we go forward. I don't have Kali pulled up at the moment to run it on to demonstrate it, but later in the course maybe I'll do that and demonstrate some things. I run those from Kali Linux. So this is ICMP that we looked at, right? They ran a ping for that address and they got responses. Now, here's a quick question. One way to remember something. In Windows, when you run this command right here, you will get 4 responses, okay? That is Windows setting. In a Linux environment, when you run this command like that, it will just keep going. We call that the ping of death. You have to tell Linux to stop, okay? Or you would run this command and then you would give it right, a number that you want it to run, okay? In other words, only do it a certain amount of times. This is again netstat running and looking at, you know, what's connected. Wireshark that we looked at. And this is Nmap, okay? So Nmap, or network mapper, that we use to scan a network and return open ports, right? What's open? Now I wanted to point something out here in this output. Those ports are filtered. What does that mean? They are behind the firewall. Meaning they're not necessarily closed, okay? But you have to meet certain criteria in order to get past the firewall, right, to access them. These others are straight open. Those two pretty much have to have open. There's port 8082, which is basically an HTTP proxy. And then port 53 is your DNS, okay? DNS is one of the most abused protocols out there. And this is, you know, Network Plus, so we won't get into all of that, but that's Nmap. And that's what it does, is it goes and looks at what machines are responding to me and what ports do they have open. All right, so quick knowledge check. What would the range of an IPv4 multicast address be in that first octet? Remember, that is a class D network. So let's just look at these for a second. A, B, C. So I'm only left with the answer, right? 224 through 229. All right. Well, that brings us to the end of this session. I appreciate you guys joining me, and you have a great day. Peace out.